Okay, welcome to another Orbiter 2010 video, and this video is going to be a continuation in my Moon to Earth to Mars video series that I'm putting together. In the last video, we took a look at how to begin thinking about setting up this Moon to Earth out to another planet plan in transects, and you can see it's not nearly as simple as a lot of the other things that we do, but we can work our way through it. The big thing to know, again, in the transects planning stage is that you can't just have the default plan for auto plan and let it do everything for you. You have to shut all that stuff off and kind of do some manual tinkering with transects in order to get this plan set up. Anyway, toward the end of the last video, we worked out how to calculate the distance, the time and days between where the moon is currently at and its antipode position. Antipode, of course, being the opposite side of the Earth from where we're going to be at periapsis. And we found that in the time that it would take to go from the place that we currently are over to here was about 9.85 days. And then it's going to take us an additional 5 days beyond that to fall from the moon down to the Earth. So that's how we were able to work out our eject date. But once you set the eject date according to what you discover there, then it changes the timing of everything, obviously. So because that timing changes, we then have to go and work out everything at least one more time. So that's what we're going to do now. We have figured out where the antipode position is at by changing scale to view over to target, and we use this line drawing tool to draw a line straight across from that position over to here. So now we are going to again bring up our triangle.
Warning, center of gravity shift offline.
The reason you're hearing that center of gravity shift offline is because the hotkey to bring this up happens to be the same as the center of gravity shift hotkey. So let me bring up that triangle again and bring it down here. This is a useful utility, but I hate how laggy it is. I don't understand why it's so laggy. Okay, so now the moon, of course, really shouldn't have changed positions at all. We should have the same number we had before, which is 218.54. Of course, it does depend a little bit on how well you place your triangle, but I'm just gonna say, well, we'll go ahead and change that angle. So 218.98, it's basically the same. So that's where the moon currently is, and now we want to know where the angle of the antipode, which in this case, it's now 357.93. So that one's actually changed, several degrees. 357.93. Now we just simply take the 357.93 minus the 218.98, and that's how we know what the angle is between the two. To simplify this for me, I actually made this little spreadsheet. Let me shut this off. I made this little spreadsheet, which just makes life a little bit easier. So 357.93, that's the angle of antipode, versus where the moon's at now, which is 218.98. And I fixed this calculation between videos. So that gives us the angle is 138.95. Now, with that angle, we can calculate the days until it'll take the moon, the number of days until it'll take the moon to reach antipode. And you can see it's actually gone up because we did some adjustment with transects. The timings of things have changed. So it went from 9.85 up to 10.54. And we now can calculate when the moon will reach antipode, when the date will be, and it's now going to be 58248.55 plus an additional 5 days that it'll take to reach the Earth. So we have a new eject date, and the new eject date is 58253.55. 58253.55. So basically about 1 day farther ahead than we currently are. So let me just adjust the date forward. .55. And you can see every time you make this change, it's going to have some small effect on this trajectory back to Earth. But you can see that, you know, each time you make the change, the amount you're changing the eject date by is less and less. So at this point, we have enough precision. We don't need to go through the whole process again. But if you were going to do this to, say, maybe try to go to Mercury, the timing to hit Mercury is so sensitive that you need to be as precise as you possibly can. So that since we've changed the date a little bit, our closest approach has changed. So we need to work with the variables a bit to bring that closer to what we want. Starting here just by taking out some outward, and that's having a big impact. And it looks like that's going to get us all the way down to Mars, basically. Just a little bit with plane change, or prograde rather. And again, you don't use any plane change at all. Okay, so back and forth here, play this little transx game. Okay, that's kind of the low point there. And let's see what happens if we go to, say, 100. Now let's go to prograde. No, that's the wrong direction. So we need to go, let's go to 100 in that direction. And kind of overshoot a little bit, go back to 100, now back to outward, take out some more outward, and we're really close there, so let's just a little bit more and we'll have it. Okay, that's Mars. We're actually below the surface there, so that's fine. Okay, now, is there anything I'm leaving out? Anything I'm forgetting? Oh, one thing I'll mention is how to do the calculation. It's really simple. So when you have the angle between the moon's current position and the antipode position, you know, just write those numbers down, just on paper or whatever. So let's 218.98. and then 348.36. And then just use a calculator to get the difference. So take 348.36 and subtract 218.98, and that'll give you the difference of 129.38. Then write that down. And make sure that you do the calculation in the right direction, by the way. Because remember, the moon is orbiting this direction. So if the moon happened to be over here, then remember it has to go all the way around this way. So in other words, your calculation should show that you have, you know, like 270 degrees or something like that. If the moon is here and the antipode position's there, and you get a calculation that says the difference is, you know, just 85 degrees or something, that's wrong, because that's assuming that the moon can go backwards, which it can't. So remember, when you're working with angles, there's 360 degrees in a circle. And if we're going to go from here all the way around to here, just make sure you do that calculation in the right direction. So once you have the number of degrees, then what you want to do is divide the number of degrees by, let me actually check real quick, by 360. So we'll take that 129, actually just put it in this way, and divide that by 360 degrees in a circle. It's a 14. And that gives us 0.35, you know, that big number there. Now we'll take that and we'll multiply it by 27.32. So take, you know, just, and again, you can just do this in a calculator, just type, you know, 0.3593888, good enough, times 27.32. And that gives you, actually I did that calculation wrong. We get this, no, that's right. Take the number, yeah, okay, so I know I wrote down the wrong number here, so that's what's kind of screwing me up. So instead of the 348.36, let me put in the 357.93, and let's redo that calculation. So simply 357.93 minus 2.18, or 218.98, that gives us the 138.95. So we put that in here, 138.95. Now take that 138.95 and then divide it by, or rather take 360 and divide by the 138.95. No, I had it right the first time. You take the 138.95 and you divide that by 360, and that gives you that number. Then you take that number and you multiply it by how long it takes the moon to orbit the Earth one time, and finally that's how many days the moon is away from that position. So I'm going to go through that again because that was very unarticulated and not very well spoken. So let's try that again. You get this angle using whatever method you want, and then you get the angle to the antipode using, again, whatever method you want. You could use a ruler on your monitor. I mean, you could actually literally put a ruler against your monitor, or a compass, or protractor, whatever. And I remember Dimitri telling me he actually used to do that. Or you can use one of those tools that I was just showing. That's actually one that Dimitri showed me. So you get the angle here, you get the angle here. Write those two numbers down. And just for simplicity, I'm putting them in a spreadsheet because I happen to have it open. But let's forget the spreadsheet for a second. Let's just do, because I don't want you to think that you have to have a spreadsheet. So let's just do this in Notepad. So let's start with moon's current position. And that's here. That's the moon's current position. So write down whatever that angle is. That's going to be 2.1898. 218.98. Then we want to know the antipode position. And again, the antipode is the opposite of the Earth's periapsis. So that's that position over there. You need to get that angle. And then in our case, it's 357.93. Now, in this case, we can simply take and subtract these numbers. You can't always do that though, and because of, you know, because if the moon was over here, then we would have to do the subtraction a little bit differently, and maybe I'll show that in another segment or something. But for this case, we can just simply take 357 minus 218. And we get the 138.95. So that's the angle degrees until moon is at antipode. It's 138.95 degrees. Now we take that number, 138.95, and we divide by 360 degrees in a circle. Simple enough. And we have 0.3859722. That should be good enough. Now we take that number, 0.3859722, times 27.32, which is how long it takes the moon to orbit the Earth one time. And we get 10.54476. That should be enough numbers of precision. This is how many days it'll take the moon to reach antipode. So days until moon reaches antipode is 10.54476. Now we take today's MJD, which is given to us in orbiter right up here, 58238.025 something 7. Today's MJD plus the days until the moon reaches antipode equals so let's do that. Let's take today's date, 58238.0257 plus 10.54476, and that gives us 58248.57046 plus the number of days it takes to fall from the moon to the Earth, which is 5. So plus 5 days. And we don't even need a calculator for that. We can just add, 58253.57046. And that equals our eject date. So that's how you work it out. So let me go ahead and close that calculator and take a look at that if you need to. But that's all this spreadsheet's doing. The spreadsheet's just simplifying my life. It lets me put in the angle of the antipode and then the angle of the moon's current position, and then it does all the other calculations for me. And then it just, spits out the eject date, which is what I need to know. Okay, now, hopefully that was a good enough explanation for how to, how to calculate that date, because the date is everything. It's so important. You can't be off by, more than, I don't know, a few hours in either direction. And if you're off by too much, then it's just not going to work. So now we can fast forward time to the antipode position, and we'll be ready to fly. Let me just take a look at the vessel here. We're on the moon. There's no need to have scram fuel, so let's dump that.
Warning, fuel dump. Warning, fuel dump. Warning, fuel dump. Warning, fuel dump. Warning, scram fuel low.
Okay, and we're going to
scram fuel depleted.
We're going to Mars, and we had a total flight time of 244 days, so we need to bring some additional locks with us. So let's go to the payload editor real quick. Yeah, here we are. Okay, so XR5 locks. Let's see how many we need. That's enough. In fact, that's more than enough. So let's actually dump some of that locks, because that's quite a bit more than we need. So let's go down to about 250 days.
Warning, locks dump. Warning, Locks
just so we're not
dump.
carrying mass that we don't need to be
Warning,
carrying.
locks dump.
We'll go with that. That's like 10 extra days. I don't think we'll have a need for anything more than that. Okay, back to this view, and now I'll go ahead and warp time forward. Get closer to the time to actually take off. And let me just double check everything one more time. Jet date. Yeah. And then the moon is going to reach antipode on 248. Okay. Just bear with me 1 second while I think. Okay, we're obviously not at antipode, so I've got a little bit of a miscalculation here, so let's work on that. So let's go back to scale the view here.
Warning, center of gravity shift offline.
And somewhere I probably just typed in a wrong number, or I'm not actually sure what happened, but at any rate, we're not at antipode at the expected time, so we just need to rework this a little bit, but it'll be easy to rework. Okay, that's where it needs to be, and you can see we're probably like a full day behind, so I probably just typed in a wrong digit somewhere. But let's just rework the calculation, though.
Warning, center of...
Bring our triangle back up, and okay, and what we want to know when the moon's current position, and that's going to be 347.12, so let's put that in. And we want to know the angle of antipode. And we're saying that's going to be 358.07. Okay, so with that information, now I can close out this triangle. We could go through, this whole process here, but again, the spreadsheet that I made does it for me. So now we have an eject date of 58.243.83. Actually, I need to put in today's MJD. That's where I went wrong. I forgot to change that. So today's MJD is 58.248. 5500. That's probably where I made that mistake. So the eject date's going to be 58.25438. So let's change that. 58.52438. It's pretty close right there. And again, we need to change our velocities in order to make up for the difference in date. And just give me a second here to find the low point. Okay, go out that way a bit. Up that way a bit. And that's probably got us hitting Mars, it does. Okay, so now we have the eject date set correctly. Now we need to warp time forward to the new date when the moon reaches antipode, which is 582498. So we need to go forward by not quite a whole day. What did I say? 0.38. Okay, we're pretty close. We still have a little bit more to do, so I don't want to bring the date all the way there, but now you can see the moon actually is at antipode, and if we do a quick comparison here, if we just want to be absolutely certain on it.
Center of gravity shift offline.
Can bring up the line drawing tool. Yeah. And straighten out this side. There we go. Now you can see when we go to this view, you can see that we're basically right at the antipode position now. But again, I left myself a little bit of time because there's still just a little bit more setup to do. But that's how you can know that you are in fact leaving at the right time. Okay, now let's close this out. Now we can come back to what we actually have to do here is we have to use a second instance of transx. We can't set up the escape plan using the primary instance of transx, and I forget exactly why that is, but for whatever reason you just can't do it. So let's bring up our second instance of transx, and we'll go escape. And on this side we'll view the eject plan, and we want the normal amount. Oops, it's the wrong. We want the normal amount of negative prograde, which is about that number. Now you can VW over to setup and go to scale to view to target, then back over to the eject plan, and that can help you fine tune, exactly where, exactly how much to put in. So somewhere around that number is going to be good enough. Then we can go back to that scale to view. And back on this side, and this is just a normal setup for going back to Earth, so we don't need to spend much time on this point. 1758 E3. And I like to have the graph projection set on plan. It just seems to look better. Now we can change the eject orientation. And we have two options. We can take this one and take a full orbit around, or we can go out that way, and I'll probably take the shorter route. But we do need to warp time forward a little bit farther, so before we finalize the escape plan, we need to keep in mind that I didn't take time all the way out to 249.338, which is where we need to be when we take off. But we're coming up on 30 minutes on this video, so I'm going to go ahead and end it here. And when we come back, I'll finish warping time forward to the time to leave, and then we'll finalize the escape plan, and we'll get this mission underway. If you liked the video, hit the like button. If you didn't like it, hit the don't like button. Subscribe to the channel if you're not already subscribed, and I will see you in the next video.